So previously, we talked about direct substitution as a way of algebraically finding limits of a function. And if you think about the example, which I have posted up here below or above, this is the previous example that we did involving direct substitution from the beginning of our 11.1 notes. And we saw that in certain cases, we could do direct substitution to easily find a limit. And in some cases, we couldn't because we ended up with something called indeterminate form. And when that happened, we had to find an equivalent limit statement here in order to find the limit of our original function. So that begs the question then, when can you do direct substitution and when can you not? Well, it really boils down to this. If your function is continuous, in other words, there are no holes, no breaks, no vertical asymptotes, then you know that the limit of your function as x approaches c is simply going to be whatever your function is at c. It's that simple. So bottom line, if your function is continuous, then you can do direct substitution. And you are guaranteed then to find the limit of your function at any given c value. So let's look at a couple of examples of this, some basic limits. So look at the function 5. Your function is equal to 5. What is the limit of this function as x approaches 3? So what we're saying is the following. We're saying as x gets closer and closer to 3, what is your function doing? Or what is your function approaching? Well, this is easy because your function is simply going to be equal to 5. Right? Your function is 5, so as x gets closer and closer to 3, we are getting closer and closer to our function is approaching 3, because it always is 3. So we can therefore just say, since f of 3 is equal to 5, right? Since f of x is continuous, therefore, the limit as x approaches 3, as x approaches 3, I should say, of 5 is equal to 5. And that gives me just a larger generality. We can say in general, the limit as x approaches c of some constant is simply equal to that constant itself. Okay? All right, let's try another one. This next one here, we can say, all right, well, we've got another function. This time our function is equal to x. Well, let's take a look at what this graph looks like. And this one's pretty simple, right? We just have a y-intercept of 0. So our slope is 1. So we're just going to go ahead and just graph something like this. All right, not great looking, but you get the idea. Make that a little larger just to cover up my mistake. So ask yourself, is this function continuous? Yeah, f of x is continuous. So if that's the case, as x approaches -2, so as we get closer and closer to -2, what is your function approaching? Well, it looks like your function would just be approaching -2, because our function is x. So since f of -2 is equal to -2, we can say the limit as, and I'll just write it over back on the left side, the limit of this function as x approaches -2 is -2. So here's another basic limit property. We can say in general, the limit of a continuous function like x, right, in this case this linear function, is simply going to be equal to whatever c is. All right, and hopefully that makes sense. Right, as x approaches -2 for this continuous function, since the function is just x, when x is -2, our function's output is going to be -2. Therefore, the limit is -2. All right, now let's look at another function. We've got x cubed. Well, ask yourself, is this continuous? Well, again, what does this graph look like? Well, when x is equal to 2, y is equal to +8. So our graph is going to just look something like this. We've got a basic cubic function here. F of x is continuous. So since f of x is continuous, you're allowed to do direct substitution for any x value. So we can say f of 2 is equal to 8. Therefore, the limit as x approaches 2 is equal to 8. So in general here, you can say, in general, the limit as x approaches c for some continuous function raised to some power, right? So these polynomial functions are going to be always continuous, assuming that, I probably should specify here, that n is a positive integer. If it's not a positive integer, then we're starting to deal with some rationals. But if that's the case, this is always going to be true. Okay? Let me just fix that a little bit. There we go. All right. Now, try a couple of these practice problems on your own and see if you can figure out each of these limits. You're going to need to review your tangent functions. So if you review your tangent functions, or remember them, you remember that they have vertical asymptotes at negative pi over 2 plus pi n radians. And so our tangent graphs are going to look something like this. Not great, but try my best. All right, so let's look at a couple of these. What is the limit of the tangent function x as x approaches 0? Now note, tangent is not a continuous function. We've got a number of different vertical asymptotes. However, it is continuous within certain intervals. In other words, from negative pi over 2 to pi over 2, this graph is continuous. So, as x approaches 0, we can just do direct substitution for this graph. We can say tangent of 0 is equal to 0. Therefore, the limit of this function tangent x as x approaches 0 is got to be equal to 0. There's our answer. Okay. And you know what? I'm going to just keep that little diagonal looking box. Looks cool. All right. The limit of this function, tangent x, as x approaches pi over 4. Now, where is pi over 4? Let me mark that over here. Pi over 4 is right around here. And you could just evaluate what tangent of pi over 4 is since it's continuous in that interval. Or you could just look at the graph, but you should see that this is simply equal to the same thing as tangent of pi over 4, which hopefully you remember is equal to 1. Okay? I didn't get the cool diagonal looking box. All right. Now, the limit of tangent of x this time as x approaches negative pi over 2. Well, look at where negative pi over 2 is. As x approaches negative pi over 2, okay, what's going on with our graph? Well, from the left side, or as we approach with the negative, this graph is approaching positive infinity. As we approach negative pi over 2 from the positive, this graph is approaching negative infinity. Well, for two reasons here, this limit does not exist. It doesn't exist because the one-sided limits aren't equal to each other, right? That's probably the biggest reason. But on top of that, even if they did agree with one another, in other words, if you had a graph where one side was approaching a positive and the other side was approaching a positive, but both of these are positive infinity, infinity or negative infinity cannot be a limit, right? So for this reason, this limit doesn't exist. I would encourage you to go ahead and open up to page 785 in your textbook and review the properties of limits if you haven't already done so. Okay, so go ahead and review those. The page numbers might be a little different if you have a different edition of the textbook, but they should still be in the same area. All right, now let's look at a few more problems now once you've reviewed those properties. If you review those properties, it turns out there are certain things that we can do with our functions. So given our functions here, f of x and g of x, if we're asked to find the limit of g of x minus f of x, you could sit there and you could try to find what the output or the result of subtracting f of x from g of x. Or you could rewrite this and say this limit expression is equivalent to the following limit expression. The limit of g of x as x approaches 2 minus the limit of f of x as x approaches 2. And why would you want to do this? Well, because quite simply, sometimes it's easier just to work with the limits than it is to work with the functions themselves. So looking at this here, what is the limit of g of x as x approaches 2? Well, sine of pi times x is a continuous function, so I can do direct substitution. So this is simply equal to what sine of 2 pi is. Now let's look at the limit of f of x as x approaches 2? Well, although that isn't a continuous function everywhere, it is in the vicinity of x is equal to 2. So we would just simply have 2 over 3 minus 2. And we would say 0 minus 2. And this limit then is equal to negative 2. And again, this is so much easier working with 0 minus 2 than it is trying to figure out what f of x, or excuse me, g of x minus f of x would be. Okay, let's try another example. This time we are finding the limit of f of x times g of x as x approaches 1/2. So again, using the limit properties, I can rewrite this and say, what is the limit of f of x? And take that entire limit and multiply it by the limit of g of x as x approaches 1/2. If that's the case, think about what the limit's giving you. We can use direct substitution to say the following. There's this first limit, and then do sine of pi over 2. And this should just simply give you 1/5 times 1, which is just equal to 1/5. So there's your limit. Okay. All right. Now, here below, I've got a couple of definitions and reminders about some specific types of functions, like polynomial functions and rational functions and radical functions. And this isn't just to recap, but just to kind of remind ourselves about the nature of these functions and how they affect our ability to apply direct substitution. I'll spare you a lot of the kind of boring details, but reminder, a polynomial function is continuous over its entire domain. Therefore, direct substitution always applies. Because a polynomial function is always continuous, you can always do direct substitution for a polynomial function. Well, what about rational functions? Clearly, rational functions are not always continuous. There are asymptotes, there are holes, there are breaks. But for rational functions then, that simply just means for any rational function, as long as our c value, where we're evaluating our limit, isn't what's causing our denominator to be equal to 0, then we can do direct substitution. Now, just like we saw above in this first example, if our c value is where there is a vertical asymptote or a hole, then you'll have to do something else to try to rewrite that limit expression. And again, you'll cover that much more in this course and in the next calculus course. But for now, just know that as long as your c value isn't what's causing your denominator to be equal to 0, then you can do direct substitution. Now, what about for radical functions? It really depends. If your index is going to be odd, then it's fair game. You can just do direct substitution. However, if your index here is an even number, right? So you're taking an even root of a function, then we just have to ensure that our c value is going to be positive. And I know that sounds complicated, me reading that out like that. So let's try a couple of examples to really hammer this home. Again, keep in your mind what type of index we have. Look at the first example. We have the limit of the square root of x as x approaches 4. We have an even index. Okay, since it's an even index, we can really only do the direct substitution if our radicand is a positive number, which it is. And since it is positive, the limit then is just simply going to be equal to the square root of 4, us applying the direct substitution, which is equal to 2. Okay, let's look at the next one. This time we have an odd index. We're taking an odd root. So if that is the case, it's fair game for us. We're just allowed to apply direct substitution because we don't have any domain restrictions here. In other words, our function is going to be continuous. So ask yourself then, what is just the cube root of -8? Well, the cube root of -8 is just -2. So that works. For number 3, we're back to looking at an even index function. So then we got to look at what's happening with our radicand. Now, unfortunately for us, our c value here is -1. So direct substitution doesn't apply. So we're then left to figure out this limit using other means. And just using the tools that we have at our disposal, the best case would be for us to just simply look at its graph. What does the square root of x look like? Well, if you recall, Square root of x looks something like this, right? It only exists. Its domain is only positive numbers. So this problem is asking you, what is the limit of this function as x approaches -1? Well, this graph doesn't exist when x is equal to -1. Therefore, this limit does not exist. Okay? So hopefully that helps give you some practice working with some basic limit properties and also being able to evaluate limits using direct substitution and really answering the question of when it is you're allowed to do that.